All right, we have much to do today. Okay, so we're at week 14 already. All right, the week before Thanksgiving week. No classes next week. All right, so today we're going to continue with chapter 7. 7.4 is the last required chapter in chapter 7, although I'll skim some ideas from 7.5 and 7.6. Okay, and we're really going to get into matrices and determinants. In fact, we're going to do chapter 8 this week. 8.1, 8.2, and 8.4 required. These other two are optional. So remember that on the homework. Okay, so 8.3 and 8.5 you don't have to do on the homework. And then after Thanksgiving week, we're going to continue on chapter 9 and chapter 10. So the final part of the class will cover chapters 7 through 10. In fact, I may still develop some materials for chapter 10. All right, and that'll be due. Ooh, I forgot if it was Friday or Monday. I got to check, but okay, but it'll be due mid-December. All right, so any questions? Any questions? All right, questions in chat? Ready to go? All right.
Hi, everyone. We're continuing with section 7.4 on partial fractions. So at the beginning, we reviewed an old school algebra example. Subtract these two rational expressions, 3 over x minus 4 minus 2 over x plus 1, get a common denominator, and you end up with this big ugly fraction over here. Now, in this section, we're going to do the inverse problem, meaning we're going to start with the big ugly fraction and decompose it like so, as a sum and or difference of nice partial fractions. We're going to find the PFD, the partial fraction decomposition, for this big ugly fraction over here. And we're going to decompose it like so. A sum and or difference of partial fractions like these, which are easier to integrate in Calculus 2, Math 151. Now, the form for this PFD depends very much on the way you factor this denominator over the reals. And that determines what case you're going to look at as you develop these partial fractions. In fact, there could be multiple cases for multiple factors. All right, let's do it. How do we find the PFD for this? Example, find the PFD, which is the partial fraction decomposition, and that's PFD, not PDF. Find the PFD for this big ugly fraction. Actually, this is the easier case because this denominator factors very nicely. We get distinct linear factors, which is the easiest case. Another reason why this example is actually pretty good is that this is a proper rational expression, meaning that it's bottom heavy by degree. The degree of the numerator is less than the degree of the denominator. The numerator, I'll type it out. The numerator has degree 1. The denominator has degree 2. The degree of the bottom is bigger than the degree of the top. This guy's bottom heavy by degree. So we have a proper rational expression here. Of course, polynomial over polynomial. It's rational, right? And we're very happy it's proper because, see, here's the thing. If the expression were improper, we'd have to use long division. And of course, we'd like to try to avoid having to do that. We would usually not use synthetic division because the denominator tends to be complicated. Synthetic division was more for simple denominators. Anyway, we have a proper rational expression. Good. We do not have to do long division. Step 2, factor the denominator. So your chapter 2 skills could come in handy here. You might have to remember factoring by grouping. Maybe you will need to remember the rational zero test, synthetic division, that could come up. Factor the denominator over the reals. This one does factor old school pretty nicely. When you factor x squared minus 3x minus 4, you get the factor x minus 4 times the factor x plus 1. And the order doesn't matter. It's okay if you switch these. Next up, because we have distinct linear factors, what will be the PFD form? What form will a PFD take? It's going to be what over what plus what over what. Have you done the homework? At least number 1 on the 7.4 homework. You should have done it by now, right? What's the form? A, which represents a real number, though unknown, over x minus 4 plus what? Plus b, let's say, another unknown real number, over x plus 1. You absolutely have to know the PFD form. Otherwise, you're not going to get this question correct. Determine the required PFD form. Get practiced on that homework, number 1. But this is the easiest case where we have distinct linear factors. In fact, we might have had 3 or 4 distinct linear factors down here, and it would have been the easier case. A bit more writing, but it would have been a fairly easy case. Distinct linear factors. Distinct means different, no copies. So again, the PFD form is relatively straightforward. A over x minus 4 plus b over x plus 1. Now, your friend might have switched the factors. And that's fine. You can switch the denominators down here. And if just the denominators are switched, that's fine. But remember that your A, your value for A will be your friend's value for B, and your value for B will be your friend's value for A. That's okay as long as your work is consistent. As long as your work is consistent with what you're doing and your friend's work is consistent with what your friend is doing. But once you decide on a scheme, stick with it. So this is one argument against copying your friend's work, which you shouldn't really be doing anyway. You want to be careful about copying other people's work because, again, your A might be their B and your B might be their A. All right. Now, again, as I said, you can switch these bottoms. There are different ways of writing the PFD form. And so far, that's been enough. Just finding the PFD form. Like on a homework problem or on an exam question, I might just ask, what's the PFD form for some rational expression? So if I were just asking for the PFD form, then you'd be done with either this or with this. But here, I'm actually asking for the PFD. Here, we actually want to find the PFD, which means we actually have to find the appropriate values for A and B. We have to find out the values for A and B that will make this whole thing work, that will make the left side equivalent to the right side. And only one real value for A together with only one real value for B, only one ordered pair of values will work. It's like you're trying to figure out a combination on a combination log. Really, it's a sequence of values. And on an exam, I would not ask you to go past D. So if you think you have to find more than 4 values, then you're not doing the problem right. On a homework or exam question, I would not make you go past D. If I want you to find the full-blown PFD. For PFD forms, I could have you go to Z. All right. Step 4. Okay, so how do we go about finding the PFD? First of all, we're going to have to find what's called the basic equation. Right, over here. And as part of your work on homework on exams, you are going to be required to state the basic equation. And in fact, If you write this down, I'll trust you that you'll be able to do the algebra in your head so that you can write the basic equation down directly from this. But if you want to be really careful, or if you're starting off and you really want to see the steps, then you might want to write this out at first. And with time, you'll be better and you'll get better at doing these things in your head. But still, be careful. Here's the left-hand side, x plus 11 over the factored form of the denominator equals, so we started with this. We started with this fraction with a factored form for the denominator, and then the PFD form over here, which was a over x minus 4 plus b over x plus 1. Now, in order to get our basic equation, which is basically a polynomial in x and the unknowns, we want to clear the fraction over here. So basically, we're going to multiply both sides by the LCD, which will be the denominator on the left. And you can think of it in factored form. So we want to multiply by both x minus 4 and x plus 1 on the left side and also on the right side. Remember, these guys are going to distribute. So both these factors will multiply into this first fraction, and both the factors will multiply into the second fraction. I apologize for the slew of circles over here. Maybe I should erase the blue circles at this point. Those aren't circles. Oh, shut up. All right. Okay. Now we're asking what will cancel out. Well, of course, we get a complete cancellation over here. These two factors knock out these two factors. You might be worried about domain issues. Don't worry about domain issues at this point. Over here, what happens? The x minus 4s cancel out. Maybe I should do this. All right, so over here, these cancel with these. We're left with 1s here. Over here, x minus 4 divided by x minus 4. We have a 1 here, a 1 here, a 1 down here, right? And then over here, what happens? This x plus 1 knocks out this x plus 1. Their quotient is 1. I don't like leaving blanks in denominators, so I like putting 1s down here, 1s up here. I like saying who's left. So then who's left? Who's left? I'll circle these in green. Who's left? Or maybe blue. I'll circle these in blue. Who's left? On the left, it's going to be the numerator, x plus 11. On the right, it's going to be a times the quantity x plus 1. And again, like early on, you can think of the who's missing trick. Remember early on, when we were first thinking about subtracting these rational expressions, we're thinking who's missing? Who's the factor I have to attach to these numerators? Well, again, the who's missing trick can also work over here, in the sense that we're asking, well, who are the survivors? Well, the a up here, and also the factors out here that are missing from the bottom. Well, x minus 4 was down there, x plus 1 was missing from the LCD that we're multiplying by. The LCD is all of this over here. Over here, x plus 1 was in the bottom. Who was missing down there? The x minus 4. That guy survives, and we attach him to the b up here. So then our basic equation, which again, you're required to write down on homework or exams, x plus 11, which was the numerator on the left side, equals a times the quantity, x plus 1, plus b times the quantity, x minus 4. And that's called the basic equation. It's going to be a polynomial in x and the unknowns. Bear in mind that if your friend switched some things around, then it will look a bit different. But both of you will be okay if you haven't made a mistake yet, and if you do proper work and you're consistent from now on. But both you and your friend can get this right. Now, we're going to solve for A and B. We're actually going to find the values we need for A and for B. And in case you're wondering why this is in chapter 7, the reason is that you could say that systems are involved, but there are some systems that are a lot easier than others to solve. So it helps to strategize. Kind of like if you're verifying tree identities, it helps to strategize. And generally speaking, when you're talking about the easier forms, like distinct linear factors down there, for the easier forms, the plugin method, the plugin values method tends to work better. All right. Now, first of all, an observation. In this polynomial, this will be true once we find the values for A and B that will work. Once we find the appropriate real values for A and B, then we're going to set this up so that this polynomial on the left will be equivalent to the polynomial on the right for all real values of X. This will hold for the appropriate values of A and B. This will hold for all real values of X. Now, this might surprise you because you might be saying, well, hey, wait a minute. I thought we had some domain problems down here, like at 4 and at -1. That's very observant, but because of a calculus argument, it's kind of an argument that involves the idea of holes. Remember those guys? But the limit still exists and all that. By calculus arguments involving like holes, actually this is true for all real values of X, even for values of X that cause domain problems up here. And in fact, in the plugin values method, actually, it's these exclusions from the domain. It's these bad guys, these bad values for X over here that will actually help us over here. We want to plug in values for X that cause us domain problems back here. Believe it or not, in some ways, they're good guys. Because what's our strategy here? We're going to use what I call the plugin method, which is easier in the easier cases, like the easier factorizations, for example, distinct linear factors in the bottom here. In the plugin method, we're going to select real values of X in such a way that at least one term will be 0. Well, think about it. Look at this polynomial here. I'll erase these over here. In this basic equation, which is really our focus now, right? In this basic equation, whatever A and B are, can you think of a real value for X that will make this equal to 0 and a real value for X that will make this term equal to 0? Well, looky here. It's actually the bad guys that were outside the domain of this fraction, right? Because a great value for X here would be -1, which was outside the domain of this guy. X equals -1 would make this whole term equal to 0. And then we're going to solve for B. Likewise over here, if X equals 4, that's going to make this term 0, and we can then solve for A. Now we do this one at a time. Don't plug in these guys simultaneously. We're going to plug this, well, we're going to plug one of these in first and the other guy second. All right. So again, ironically, it's actually the values excluded from the domain that's going to make things nice for us. We like to choose values of X. They tend to be these guys that will make the coefficient of A or B equal to 0. These other pieces equal to 0. All right, so we're going to plug in -1. I'll plug in -1 first, but of course the order doesn't matter. I'll plug in -1 first, and then I'll plug in 4 second. Okay, so let's first plug in X equals -1 into both sides. So you have to plug in -1 on the left side and -1 into the right side. Wherever X appears, you substitute with -1 in parentheses, potentially in parentheses. Here, that's not so necessary, but to be safe, you may want to consider parentheses. In fact, here I didn't use parentheses. X is -1, and then plus 11 equals, okay, bottom line, if you plug in -1 for X, you should realize that X plus 1 will be 0, and therefore A times 0 will be 0. right? You don't have to show that work. So you can plug in x equals -1 here. And in fact, you don't have to write anything here. Okay, I will believe you if you just have this disappear, and I'll know that this term becomes 0 when you plug in the -1. Over here, when you plug in -1, this term does not die out. We have to work with this. So what do we get? On the left, hey, if you're in Vegas, you lose $1. Well, I guess you'd be a laughing stock if you just lost $1. But if you lose $1 and you win $11, you've won $10. This totally disappears. I wouldn't even have to see this, right? And then over here we have b times -5 or -5b. Divide both sides by -5. Don't subtract. Some people subtract. Divide by -5. You want to divide. Turn it around, and we get b equals -2. We have solved for b. So unless I've made a mistake, I know that b will be -2. It's just a matter of what a is going to be. Next up, let's plug in x equals 4. It's a similar process. Plug in 4 into both sides, all right? 4 here, 4 here, 4 here, right? 4 plus 11 will be 15. Over here, we're going to get 5a. What happens over here? You plug in 4 for x. You get 4 minus 4 equals 0. b times 0 is 0. This totally dies. You don't have to show any of this. If you just write this, that's fine. 15 equals 5a. Divide by 5. Switch sides. a equals 3. Now you might be asking, well, hey, where's the system? Well, a equals 3, b equals -2. It's right there. a equals 3, b equals -2. Now you're not done yet, folks. You're not done yet. Kind of like with variation, where you had to plug in for k. Remember that? You have to plug in the values. Method 2, the matching coefficients method, I'll discuss later. Method 2 is a more complicated method here. And in fact, in the method 2, you would actually have to solve a full-blown system, which you could do, and I hope you could do. But I'll discuss method 2 in the more complicated examples where it might actually be superior and more concise. But whatever way you do it, you can get the correct values for a and b. You're going to get a equals 3 and b equals -2. And either method will give you these two values. Plug them in. Write out the PFD. Now, you don't have to rewrite this, but this is a reminder, okay? In your final answer, I would accept this as your final answer, or maybe even that. Okay, so we plug in a equals 3, right? And again, focus on your own work, because remember, your a might be your friend's b, and your b might be your friend's a. So focus on your own work, right? Our a was 3, remember? Our b was -2, right? So we get 3 over x minus 4 plus -2 over x plus 1. However, it is conventional that if we have a negative constant up on the top, it's conventional to pop out a -1. So it's more conventional to write this. 3 over x minus 4 minus 2 over x plus 1. Now, if your friend did some switching up, your friend might have gotten -2 over x plus 1 plus, there's an implied plus sign over here, right? 3 over x minus 4. And if your friend showed good work and all, your friend would be just as correct. So we're correct and our friend is correct, assuming you've shown appropriate work. These are both perfectly good. There might be a slight preference to want to minimize the use of these symbols. So this might be preferred because we just have to write one of these major signs here, but I say this is perfectly good. Yay for both of you. And hey, you can check your work, right? That's an old algebra problem. It's what I showed you early on. Get a common denominator, build these back up, and you should get back up to this over here. You could check your work, although that may take some time. In a way, it might be faster just to take a piece of scratch paper or the back of an exam and just redo the work from scratch. Redo what we just did from scratch. But another way to check is that you could combine these like in old school algebra and try to get back here. But that's not necessary. Okay, it's not like a log equation problem. You don't have to check your answer, but of course you feel really good if you can verify it somehow. All right. So we have worked out our first PFD. Our PFD, our partial fraction decomposition, that's a lot to say, for this guy is this or this. And in Calculus 2, you can integrate term by term, and you can integrate these term by term. Later on, more complicated cases, and we'll also talk about method 2 on matching coefficients next time.
All right, any questions before we go on? That was a lot. That was long, right? Because we were doing our first one, introducing these ideas. Any questions before we go on to more cases? We're going to hit these examples. Any questions? Any questions? All right, we're going to go through these examples.
Hi, everyone. We're continuing with finding PFDs, partial fraction decompositions for rational expressions. Now, before, we dealt with the easiest case when the denominator could be factored as a product of distinct linear factors. Here, we have repeated linear factors, or powers of a linear factor. The cube of x plus 2, basically 3 copies of x plus 2 multiplied together. So this case will be a bit more complicated, and the form will be a bit trickier. That's why it's very important to know how to write down the correct PFD form. If you don't know the form, you're dead. First off, I want to know if this rational expression is proper. Is it bottom heavy by degree? Well, what is the degree of the numerator? The degree of the numerator is 2. Now, look at the denominator. If you were to expand this, if you work out the cube, what would be the leading term? You don't have to write out the other terms. Just ask yourself, what would be the leading term if you were to cube x plus 2? The leading term would be x cubed, and then you would have lower order terms. But bottom line, what degree is the bottom, the denominator? That degree is going to be 3. So this will be proper. It will be bottom heavy by degree. So remember, when you see something like this, imagine expanding this out, but you only have to really worry about the leading term. You don't have to write out or worry about the lower order terms. So imagine that these are written out in descending powers or before determining the degrees. Again, we're happy that this is proper because it means we do not have to do what? We don't have to do long division. As much as long division is fun, we love long division, we don't have to do it here. Sorry. Step 2, let's factor the denominator over the reals, but fortunately, it's already been done for you. The cube of x plus 2, that's already factored. Now, bear in mind, I have the right to give you a problem where I have this expanded out, x cubed, yada, 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 and then it's your job to factor it back to the cube of x plus 2. That's fair, okay? You'll have to remember chapter 2, right? Maybe the rational zero test and synthetic division to get the factorization, but that would be fair to go backwards from here to here. But in this example, I'm being nice. I'm giving you the factored form of the denominator. You're welcome. Step 3, determine the required PFD form. Now, this is going to get a lot of people in trouble, but you have to know what the PFD form is if you have any chance of getting this problem correct. How do we deal with repeated linear factors? Remember, the key idea is that with the denominators, you do what? With the denominators, you run up to the power. Here, you're going to run up to this cube. Now, of course, since you've done the homework, 7.4 number 1, I'll give you 10 seconds to write down the form. You got it? All right, repeated linear factors, we run up to the power. Remember, A, B, and C represent real numbers that are unknown at this point. We run up to the power. A over x plus 2, all to the first basically, plus B over the square of x plus 2, plus C over the cube of x plus 2. That's what I mean by running up to the power. If we had a fourth power down there, we'd have another fraction with the fourth power down there. Now, if you wish, or if your friend wishes, your friend could have written the PFD form basically in reverse. So maybe your friend puts the cube down here, keeps the square here, puts the first power guy or first degree guy down here, over here. That's okay. There are various ways to write the PFD form. Maybe your friend likes to decrease the power. That's fine. So there are different ways of writing the PFD form, but you basically have to have something like this, where you have unknown real constants on the top and the first, second, and third powers of x plus 2 on the bottom. And you can reorder these fractions. That's fine. Now, it turns out that there is only one ordered triple, a real value for A, a real value for B, and a real value for C that will make the right side equivalent to the left side. Remember, all of these are simpler than this. This had x squared over the cube of x plus 2. Even this guy has just a number over the cube of x plus 2. And these will be easier to integrate in calculus 2. Incidentally, as long as this thing is bottom heavy, it does not matter what this polynomial is. It could be 1, it could be 7, it could be 3x minus 5, it could be x squared plus 4x minus 2, whatever. As long as it's bottom heavy, if you have any non-zero polynomial on top, here's the breakdown. Here's the PFD form. Okay, step 4. We need to obtain the basic equation. In order to accomplish that, we multiply both sides, basically every term on both sides, by the LCD, which is always going to be the denominator on the left-hand side. We multiply by the LCD, this denominator over here on the left. Now, hopefully you can do this mentally, but if you wish, you can, of course, write out the cube of x plus 2, the cube of x plus 2, the cube of x plus 2, and the cube of x plus 2, and see how things cancel out. That takes a fair bit of writing, but if that really helps you out, then go ahead and do it. But we hope we can do it mentally, right? If we multiply a fraction by its own bottom, we get the top, x squared, equals. Again, we're multiplying all these fractions by the cube of x plus 2. Right? It might help if I kind of move this guy around, kind of like a ghost.
By the way, one note, let me make a comment. In rare cases, there might be a simplification to be had, but that's in rare cases. If you have a common factor, a good common factor on the top and the bottom. That's rare, though.
I'll do this. All right, so we multiply this first fraction by the cube of x plus 2. We have 3 copies of x plus 2 over here, 1 copy of x plus 2 over here. What happens? A pair of x plus 2's cancel, but you still have 2 survivors up here with the a. So we have a times the square of x plus 2. The third factor here gets canceled by this guy. What if we multiply the second fraction by the cube of x plus 2? Well, 2 pairs cancel out, 2 pairs divide out to 1. We have 1 copy of x plus 2 left, and that attaches to the b. So plus b times 1 copy of x plus 2. Plus, what happens if we multiply the third fraction by the cube of x plus 2? Well, here, just like with the left side, this cube of x plus 2 completely cancels out with the bottom over here, completely cancels out the bottom here, and we're left with c alone. All right, plus c. So that's going to be our basic equation. Remember, you must write the basic equation as part of your work. Now we're going to use the basic equation to find the values we need for A, B, and C. So remember the strategy we used last time in method 1. Do you see at least one real value for X we could use that will zero out some of these terms? Look at this. What value for X would really help us here? I think -2. Ironically, -2 was the one number outside the domains of these guys, but actually that's the number we want to plug in. Remember, the basic equation holds true for all real values of X, including the exclusions from the domains up here. In fact, those exclusions are the guys we want to plug in. So let's plug in X equals -2. Okay, we plug it into both sides, the left side and the right side. Again, here's the basic equation. We plug in -2 on the left. Now, folks, when I plug in -2 on the left, do I get this? Oh, -2 squared. Be careful. For once, we really need these grouping symbols. Whenever you perform a substitution, be prepared to put grouping symbols, especially when you have these negative signs involved. So we want the square of -2, which is what? That's going to be +4 on the left side. Over here, what's going to happen when we plug in -2? Well, basically we get a 0 term here, right? Plug in -2, we get a 0 term there. Look at this. I mean, you don't have to show all this work. Basically, tell me you're going to plug in X equals -2, and I'll believe you. C equals 4, right here. C equals 4. In fact, if you say X equals -2 and write down C equals 4, I'll believe you. Okay. I hope you're careful with this mentally. Again, the square of -2 is +4. These are zeros, 0 terms. C over here. C equals 4. All right. Now, assuming we haven't made any mistakes, C is 4. If we haven't made any mistakes yet, and we haven't, then C will be 4. So you know what? We can go ahead and plug that in. We can update the basic equation. And that's actually a really good idea because it helps remind you that we know what C is. We know C is 4. So let's run with it, right? Let's run with it. Because if you forget that we know the value of C, then you might end up doing a lot more work than you have to. We know C is 4. So let's use it. Let's plug him in. He's no longer unknown. Okay, at this point, we can either stick with method 1, the plugin method, or we could switch to method 2, matching coefficients. But let's save that for later. As some of you might prefer method 2 here when you learn it, but let's stick with method 1 for now. Method 1 can still be okay. In principle, both methods work for all of these problems. All right, we already plugged in X equals -2. We'll just use your numerical sense, right? Look at these things. What are some other nice values of X to plug in? And there are no wrong answers. You could, in principle, be weird and plug in pi, although I wouldn't recommend that. Or your SSN, I wouldn't recommend that for all sorts of reasons. But what would be some nice values of X to plug in to make this simpler? Okay, let's try plugging in values. I think X equals 0 would work out. For one thing, we know 0 squared is 0, all right? I think 0 would be a popular choice. All right, so let's plug in X equals 0. We get 0 squared, or 0, on the left side. You don't have to show this work here. I mean, if you show me the next step, 0 squared is 0, okay? 0 plus 2 is 2. 2 squared is 4. That's 4 times A, plus 0 plus 2 is 2. So we have 2B over here, plus the 4. We could clean this up. We can divide both sides by 2 and switch sides. So the zero's on the right. Divide this by 2, we get 2A plus B plus 2 equals 0. And then it might look more natural to us if we subtract 2 from both sides and we have our non-zero constant on the right side. You don't have to do that, but I think we're more familiar with this form. 2A plus B equals -2. A nice linear equation in A and B. Okay, that's nice, but what's A and what's B? We're going to need another equation. So we're going to have to plug in a third value of x. Remember, we plugged in x equals -2. We plugged in x equals 0. Can you see another value of x that would work out nicely? Many of you might say 1, and that would work out fine, but you know what's even nicer? How about -1? Because that'll make these guys really nice, although you have to be careful over here. If you're not careful with signs and parentheses, maybe +1 is better. But if you're like me and you'd rather have easy arithmetic, -1 actually works out nicer. Okay, so let's plug in x equals -1. On the left side, be careful, it's the square of, put the -1 in parentheses because you're going to end up with +1 on the left side. The square of -1 is +1. Over here, okay, basically -1 plus 2, that's 2 minus 1, or 1, right? The base here is 1. Same with this guy over here, it's 1. Okay. Well, 1 squared is 1. We have 1a, or just a, over here, plus 1b, or just b, plus the 4. Let's subtract 4 from both sides. We get -3 equals a plus b. Switch sides, and we get a second linear equation in a and b. Now we know from before that c equals 4. We got that from before. And now we have these two linear equations in two unknowns, a and b. Guess what? We have what S word? We have a system. And that's, again, a key reason why this stuff is in chapter 7. Actually, author Ron Larson used to have this partial fraction stuff back in chapter 2 because he thought, well, if we're talking about rational expressions in chapter 2, that's a good time to bring up this stuff. But then he realized in one of his later editions of his pre-calculus book, wait a minute, they have to know how to solve systems. So maybe chapter 7 is better. Anyway, you solve this system. It shouldn't be too hard. You could use substitution or the addition method, multiply this bottom guy by -1 on both sides, and then add, basically subtract equations, right? And you end up with a equals 1 and b equals -4. Try to show the work if possible. This system is not too bad. You can use the methods from early in chapter 7. So remember, c was 4. We already got that from before. And we now have values for a and b. A equals 1, b equals -4. Remember, c was 4. Are we done? Are we done? Not quite. We have to plug these values in. This was the PFD form. Plug in 1 for a, -4 for b, and 4 for c. 1 over x plus 2 plus -4 over the square of x plus 2 plus 4 over the cube of x plus 2. And I would accept that. Although, if your number up here is negative, it is conventional to factor or pop out a -1 factor. So we would normally write this as 1 over x plus 2 minus +4 over the square of x plus 2 plus 4 over the cube of x plus 2. Either is fine, as far as I'm concerned. If your friend wants to write these in reverse order, that's fine. This fraction minus this fraction plus this fraction, that's perfectly okay. You can rewrite these fractions in a different order as long as the appropriate signs are attached to the fractions. And again, if you want, you could check this. A check is optional, either by building these fractions up, getting a common denominator, and then you should get this back. Or it might be easier just to take a blank piece of paper, scratch paper, and just rework the problem from scratch and make sure you haven't made any mechanical errors. On an exam, I'm normally pretty lenient as far as mechanical errors go, but I really hope you get the right PFD form and that you show me that you know what you're doing, that you know appropriate methods. But if you make a small arithmetic error, I tend to be fairly lenient because I don't really expect people to check. It feels good when you see this in a check, but I don't expect people to check. So far, I've talked about method 1 for finding A, B, and C using a plug-in or substitution method, finding nice values of x to plug in, and maybe solving systems. In method 2, we're going to discuss the matching coefficients method. And the harder that denominator gets, the more complicated that factorization in the denominator gets, the more complicated a form you get, and then the more you want to shift from method 1 to method 2. You can always use a hybrid, and both methods will work entirely in all these problems. But later on, in our next example, we're going to start mixing the methods, and we're going to look at the matching coefficients method. Okay, next time.
Any questions thus far? Any questions thus far? You're going to get lots of practice on the homework. I go through like, I don't know, T or something. I almost went to Greek letters. All right, any questions so far? Okay, questions in chat? Let's proceed.
Hi, everyone. Continuing with finding PFDs, partial fraction decompositions. In this part, we're going to look at denominators that have distinct R-irreducible quadratic factors, or quadratic factors that are prime over the reals. You cannot factor them further over the reals. So for example, we'll look at this, 1 over x squared plus 1. X squared plus 1 is an example of a quadratic factor that's prime over the reals. Try factoring it. You can't with just real coefficients. And we don't count x plus I and x minus I because you have imaginary numbers. X squared plus 1 is prime over the reals. You know that a quadratic is prime over the reals if it has no real roots, no real zeros, and there is no real value for x that makes the bottom equal to 0. So here's an example of such a factor. Now, if you consider the fraction 1 over x squared plus 1, well, there's not much to do there. This is just a basic partial fraction in and of itself. So this fraction itself cannot be decomposed further using a PFD. In fact, in calculus 2, you're just going to integrate this directly as the inverse tangent of x plus c, a constant. In fact, you'll see that in calculus 1, math 150. The integral of this is the inverse tangent of x, or the arctangent of x, plus an arbitrary constant. By the way, you use integrals when you find things like areas under a curve. Okay, right. So there's nothing to do here. If you have 1 over x squared plus 1, there's nothing to do. But now, oh boy, we have a lot to do here. Find the PFD for this big ugly guy over here. So this is going to involve a lot of work. In fact, right off the bat, what's different about this rational expression? Why is this going to be a lot more work? What is the degree of the numerator, the top? The degree of the numerator is 4. What's the degree of the denominator? Only 3. This thing is not bottom heavy. So we're going to have to do what? Use long division.
I should have put a D down there. The degree of the denominator D is 3 down there.
Now on homework and on exams, I'm not going to have you make a big mess of that. So don't worry. You don't have to do a whole bunch of intense long division on the homework or exams. But I will say that, I expect you to remember the days of long division, know of long division. This thing's improper. The degree of the bottom is not bigger than the degree of the top. Oh, oops, by the way, that's a D. All right, the degree of the denominator is not bigger than the degree of the numerator. This expression is improper, which means that we have to do long division. Remember, use synthetic division if the bottom is very simple, like x minus 3. Now, when you do the long division, you get this, right? Okay, so you put the divisor over here, right? You put the numerator in here as the dividend, work it out. And it turns out that you get x minus 1 as your quotient. You get 7x squared plus 9 as your remainder. And then the divisor is copied over here. Remember, if you complete the process here appropriately, remember that your remainder is either going to be 0, in which case you just have a polynomial, right? So either the remainder is going to be 0, which is really great, or you have a remainder whose degree is less than the degree of the divisor. So if you perform long division correctly, then you'll either get 0 here, or you're going to have a rational expression that's bottom heavy, that's proper. So even though this original expression is not proper, this expression over here is proper. If you do your long division correctly, then this will either be 0 or it'll be a proper rational expression. And we're going to perform a PFD on this. Find a PFD for this piece. But keep this part here, the quotient, that polynomial quotient here, keep it in the bank. Remember it. Keep it in the bank. Don't forget it. You will have to write them in the end. All right, in step 2, factor the denominator here over the reals. Here we factor out the GCF, which is x. Well, I don't want to say ignore. Let's set aside the polynomial part for now. Right now, it's a ghost. X minus 1 is a ghost that's hanging over everything, but we're going to focus on this proper rational expression. When you factor out an x, you get 2x squared plus 3 as the other factor. And notice the structure here. How does the denominator factor? We have over here, in x, we have a, what kind of factor? We have a distinct linear factor. That's the x. And what's the deal with a 2x squared plus 3? It's not linear. It's a distinct, I won't type distinct here, but it's a quadratic factor that is prime over the reals. How do we know it's prime? Look at 2x squared plus 3. This has no real zeros. If you don't believe me, try taking the discriminant, right? The discriminant would be negative. Or just think about it, right? In order for 2x squared plus 3 to be 0, then the 2x squared here would have to be negative 3. And then you might be able to see that there is no real value for x where you're going to get a negative 3, because the square of a real number is never negative. All right. So here, now again, up here, if we just had a prime quadratic in the bottom, for something like this, there was nothing to do. This was a perfectly good rational partial fraction, and you can integrate it right now, actually. Or when you take calculus 2 or 1. But over here, okay, we have a mix here between a distinct linear and this prime quadratic over the reals. In step 3, we need to remember the form, okay? And it's going to be the same form regardless of what the top is, as long as it's a polynomial such that this guy is bottom heavy. So it doesn't matter if it's a 1 or an x minus 3 or something like that. All right, what's the form? I'll give you 15 seconds to remember. Write down the form. All right. Again, remember x minus 1 is a ghost. We'll need him at the end, the quotient. Now, when you break this guy up, it's going to be a over x. That's because of the distinct linear factor over here. And because of this prime quadratic over the reals, we put the 2x squared plus 3 down here, and we need to put a linear form up on top. Remember, what was slope-intercept form for a line? It was y equals what? mx plus b. Basically, a number times x plus a number. So most students would write bx plus c. Of course, you can switch these fractions. You can mix around the letters, but basically you need this as your PFD form. And remember the x minus 1. That's a ghost. That's in the bank. Okay, now we need to find the basic equation. And we find it by multiplying both sides by the denominator here, the LCD. What happens? In fact, take some time to write it out. The basic equation. Okay, when you multiply this fraction on the left by its own denominator, you're left with the numerator, the top, 7x squared plus 9. That's always going to be the case. By the way, again, x minus 1 is a ghost up here. All right, equals. Now, we're multiplying both of these terms, both of these fractions, by this denominator, the LCD. If you multiply this fraction by this denominator, the x's knock each other out, and you have the 2x squared plus 3 remaining together with the a. Plus, okay, so when you multiply this fraction by this denominator, the 2x squared plus 3's knock each other out, and you still have an x. Now be careful. A lot of students do this. And it's unfortunate when it happens on the final. A lot of students write, okay, I have my bx plus c, and I'm going to multiply by x. Well, what do you think? You got to multiply all of this by x. Use grouping symbols. And a lot of students forget that. They're so tempted to write bx plus cx, they forget the grouping symbols. You need these. It's the quantity, bx plus c, all times x. Remember that a fraction bar implicitly groups the numerator and the denominator. So sometimes it helps to actually write these out. Okay, and this is our basic equation. Again, x minus 1 is a ghost up here. Don't forget about him. We have our basic equation. We're now going to use it to solve a, b, and c. Remember that the basic equation holds true for all real values of x. Now, we're going to try a hybrid, a blend of method 1 and method 2. Method 1 was the plug-in or substitution method. Can you find a real value for x such that when you plug it in, you can make one of these terms especially really nice, maybe 0? How about x equals 0? In fact, more than any other value, 0 is going to work out really great on the right-hand side. What happens when you plug in 0 on this right side? And you also have to do it on the left side. But over here, look at this. This term here is going to be 0, and that helps a lot. That kills the b and the c. And you can solve for a. Plug in x equals 0. On the left side, you have 7 times 0 squared plus 9. That's just 9. On the right side, when you plug in x equals 0, okay, you get basically 0 plus 3 is 3, and that's times a. You get 3a, plus this whole term dies out. That's a big old 0 here. 9 equals 3a. Divide by 3 on both sides. What's a? A is 3. And assuming you have not yet made a mistake, a lot of people make a mistake with the form up here and also the parentheses, but assuming you haven't made a mistake yet, a equals 3, that's in the bank, along with this guy. So it might be a good idea to rewrite the basic equation with a equals 3. Now, for those of you who might say, oh, come on, Ken, that seems like a waste of my time. No, because if you leave that as an a and you forget that you know a's value, you could end up wasting a lot more time in the end. Imagine trying to solve a system of 3 linear equations and 3 unknowns when you didn't have to. We know a is 3, okay? So let's plug it in. A is 3. A is 3. And this is the revised, updated basic equation. I won't mark you down for not doing this, but it's a really, really good idea, because if you don't do this, you're going to forget a is 3, and you are in danger of doing a lot more work when you don't have to. Appreciate what's in your bank. That's always the case. All right. Again, let's keep reminding ourselves x minus 1 is a ghost. Now, how can we find b and c? Now, we can keep pushing method 1. You can always keep pushing method 1. Use other real values for x, maybe 1, maybe -1, maybe 2. But basically, you can plug in maybe a couple more values for x, and you can solve a system. You can do that. And if you do it right, you can get the right answer, right? But some students might say, you know what? I'm itching to do some algebra here. I don't want to plug in other numbers. Let's go ahead and do some algebra. All right. What D word are you thinking? I'm thinking distribution, the distributive property. Let's do some algebra. So with matching coefficients method, we're going to start by using some algebra. Now, at some point on the left side, I'm going to indicate the missing term, like we did for synthetic division. Notice that there's no x term in here. Here, I'm going to write out that missing term, the plus 0x. You don't have to do it right here, but you should do it eventually. Now we're going to use the distributive property. 3 times 2x squared is 6x squared. 3 times 3 is going to be 9. X times bx is going to be what? X times bx is going to be bx squared, and x times c is going to be cx. So I've distributed within both of these terms. Now we're going to combine like terms on the right. And you might be going, well, what do I mean by that? I'll give you a hint. Whoops. All right, now, what if I ask you, what is 3x plus 4x? Right off the bat, you'd say, oh, I know that. That's going to be 7x, right? But what did you do? As you were working this out, what did you do? Basically, you were really factoring out the x, right? You have 3 plus 4 in here, and you combine the coefficients. You knew that 3 plus 4 was 7. 7 times x is 7x. So in a way, you were factoring mentally, and you used the fact that 3 plus 4 was 7. That's how you combine like terms. Likewise, over here, take a look here. We have 6x squared. I'll switch to blue, actually. We have 6x squared, and we have bx squared. Folks, these are like terms. B is a real number. It's just unknown. Those are like terms over there. The 6x squared and the bx squared. What's 6x squared plus bx squared? It's like a local factoring. With these guys, you factor out an x squared. And then what's the other factor? You combine the coefficients, 6 plus b. It's basically factoring. When you combine like terms, you're doing a factoring, like over here. 6x squared plus bx squared is the quantity 6 plus b all times x squared. You're combining like terms, like over here. Plus, okay, what's the x term? It's c times x. I like to put parentheses around the coefficients, whether you have 1 term or 2 or whatever, plus the constant term, a 9 over here. Again, I'll put that in parentheses. Now, over on the left side, I'm also going to separate out the coefficients in parentheses. 7x squared is 7 times x squared. 0x is 0 times x. If you didn't write the 0x here, put it here. 9 is 9. Put that in parentheses. So what's this method? Our method 2 for finding B, C, and so forth. What's our method here? Matching coefficients. Here's the idea. We need the polynomial on the left to be equivalent to the polynomial on the right. These are both written in descending powers of x. The only way that you can have equivalence is if the coefficient on x squared here equals the coefficient on x squared here. So we match those coefficients. In fact, let's match them up right now. We have 7 equals 6 plus b. 7 equals 6 plus b, all right? And then we match the coefficients on x. 0 equals c. That sounds great. 0 equals c. And we match the constant terms. 9 equals 9, which is not very informative. So if we have a solution, we need 9 equals 9. Well, that doesn't help us very much. And by the way, if you get something like 9 equals 8, you know you made a mistake. So we're matching the coefficients on the like terms here. The coefficients on x squared, 7 equals 6 plus b, then 0 equals c, then 9 equals 9, which doesn't help us. But again, if you get like 9 equals 8, you know you made a mistake somewhere. But looky here, we have here a what? We have here a system of really two linear equations in two unknowns here, but this is a very, very easy system to solve. Let's do it. So 7 equals 6 plus b, well, b equals 1. 0 equals c, well, c equals 0. And what do we have in the bank? Remember, we had the x minus 1 from long division. And from before, when we plugged in x equals 0, we got a equals 3 from method 1. And for method 2, we're getting these two values here. We're combining the methods. It's like a hybrid. So put it all together. We're not done yet. Put it all together. Write out the PFD. Now remember, this x minus 1 here that we got from the long division, don't forget them. This big improper fraction, when you divide, you get this polynomial quotient, x minus 1, from the long division, plus, and then when we broke up that proper piece, that proper piece was way up here, and then we, the proper piece was way up here, and then we factored the bottom, right? But basically these guys, okay, we end up with this, a over x plus bx plus c all over 2x squared plus 3. Remember, we got a equals 3, b equals 1, c equals 0. All right, so we get x minus 1 plus 3 over x plus 1x plus 0 all over 2x squared plus 3. And what is 1x plus 0? It's just x. So in the end, we have x minus 1 plus 3 over x plus x over 2x squared plus 3. And this is easy to integrate. I mean, if you're going to integrate this, integral dx, you're integrating this with respect to x. This would technically be fair as a Calc 1 problem, actually, Math 150, but your Math 150 teacher would have to be a little sneaky, expecting you to know partial fractions like this, but it would be fair, all right? It's always easy to integrate polynomials. It turns out the integral of 3 over x is 3 times the natural log of absolute value of x plus a constant. And then when you integrate this fraction here, you do a u sub. You let u be the bottom, and you apply integration by u substitution. We can integrate this thing term by term. Next up, the hardest case for the denominator, which involves repetitions or powers of prime quadratics. Really, I'm talking about powers of guys like these, 2x squared plus 3. Next time.
All right. Any questions thus far? Any questions thus far? So we'll do one more video, then we'll take a well-deserved break. Okay, that last example.
Hi, everyone. In our last example, we're going to find the PFD, the partial fraction decomposition, for this rational expression. Don't worry about the fact that this top is complicated. That doesn't hurt us so much. Our first question is
actually, folks, you know what? This video is going to last 21 minutes. I say, let's take a break now. Let's take a break now. All right. So let's take a break now, and then we'll come back at 8:25. Okay. So let's take our break. Come back at 8:25. Unmute, because we're going to mute now, right?
Interesting question.
Yes, it is. Be quiet, Siri. Should be nicer than my personal assistant, but all right. I'll see you at 8:25 then. Okay, mute.
Hi, everyone. In our last example, we're going to find the PFD, the partial fraction decomposition, for this rational expression. Don't worry about the fact that this top is complicated. That doesn't hurt us so much. Our first question is this proper? Is this bottom heavy? What do you think? The degree of the top, the numerator, is 3. But what is the degree of the denominator? If you were to expand this out and write it in descending powers, what would be the leading term? The leading term would be x to the 4th. And then you would have lower order terms. But what degree is the bottom? The degree of the denominator, the bottom, is going to be not 2, but 4. Is this bottom heavy? Yes, it is. Ultimately, this is bottom heavy. The expression is proper rational. Bottom heavy in degree. And that makes us happy because we don't have to do what? We don't have to do long division. Proper, bottom heavy, good. All right, factor the denominator over the reals. Well, we've already done that. Although, again, it would have been fair for me to give you the expanded form and you factor back. But so far, so good. We don't have to do long division. We don't have to factor the bottom. But then here's where it gets harder. What is the PFD form? Now, don't worry so much about the top. That could have been a 1 just as well. This thing is bottom heavy. This could have been a 1 just as well. When it comes to figuring out the PFD form, we have here repeated or powers of a quadratic factor that is prime over the reals. This quadratic has no real zeros, x squared plus 1. What is the form? It's going to be what fraction plus what fraction? Two hints. Hint number 1. You want to run up to the power in these denominators. And that's a square over here. So we have 2 fractions. On the top, because we're dealing with powers of a prime quadratic over the reals, up here in the tops, we are going to need linear forms. Think slope-intercept form. Write out the PFD form. All right. Here it is. So we run up to the power. In the denominators, we have x squared plus 1, all to the first, basically, and then x squared plus 1, all to the second. If that were a cube over there, we'd need another fraction that looked like these guys with the cube on the bottom. And in the top, we need linear forms. Remember, slope-intercept form was y equals mx plus b, right? So these tops are going to look like the mx plus b. A number times x plus a number, ax plus b. Over here, cx plus d. Your friend could switch the denominators, that's fine. Here, I run up to the power. Next, in step 4, we need to write the basic equation. So we need to multiply both sides by the LCD, which is going to be the denominator, the bottom, on the left side. Now, when you multiply this fraction on the left by its own bottom, you're left with the top. So the left side of the basic equation will be the top, the numerator here. Let's focus on the right side because a lot of students make mistakes on the right side. You're multiplying these 2 fractions by this LCD. Do it. I'll give you 20 seconds. Try to write the right side of the basic equation. All right. So again, on the left side, when you multiply a fraction by its own bottom, you get the top. Make sure not to miswrite the top. 2x cubed minus x squared plus 2x plus 2 equals, okay, we're multiplying this fraction. We're multiplying this fraction by x squared plus 1 all squared. So we're multiplying this fraction by 2 copies of x squared plus 1. When we do that, well, one of these cancels out with one of these, but one of these factors still remains. So we have an x squared plus 1 factor still remaining up there. And we multiply that factor by the ax plus b. But remember, folks, you need grouping symbols. You're multiplying all of ax plus b. Remember, the fraction bar implicitly groups its top and its bottom. Here we didn't need the parentheses so much. Here we need the parentheses. It's the quantity ax plus b times the quantity x squared plus 1. You need parentheses around both these factors. Plus, then we multiply this fraction by its own denominator. You're left with the numerator. Here I put parentheses, but since there's a plus sign in front and it's just this guy, right, then we didn't need the parentheses here so much. Still, I wanted to play it safe. Plus the quantity cx plus d. But watch out, a lot of students make mistakes with this part over here. You need grouping symbols. Now, we need to find the values for the 4 unknown parameters, which are A, B, C, and D. And on homework and exams, if I ask you to write out the PFD, not just the PFD form, I won't go further than D. Okay, so at most 4 parameters here to solve for. Now, before, we relied heavily, or we at least started with method 1, where we plugged in convenient values for x. But here, there are actually no super convenient real values for x, and that's unfortunate. Now still, in principle, you could pick 4 real values for x, plug them in, and you'll get a system of 4 linear equations in 4 unknowns. But you run the risk of that system being a bit uglier than you'd like. Well, as it turns out, if you play it straight, that system may not be too bad, actually. But it could be worse than you need it to be. So here, I think I'll actually start with method 2. We're going to go all the way with method 2. We're going to start off straight up with the algebra. We're going to distribute like crazy here, do the FOIL thing, right? And we're going to combine like terms. And we're going to match coefficients. So we're going to start with method 2, the matching coefficients method. Although if you love method 1, you could do it that way, but be prepared to solve a system that's a bit bigger and more complicated than you might like. All right. So, well, go ahead and do it. Give you 20 seconds. Foil this thing out. Okay. AX times x squared is AX cubed. AX times 1 is AX. B times x squared is BX squared. And B times 1 is B. And then you have these guys here. Bring it all together. All right. So we have on the left that original numerator, 2x cubed minus, I went ahead and put in a 1 here. Minus 1x squared plus 2x plus 2 equals, again, ax cubed plus ax plus bx squared plus b from the foiling, plus, don't forget, the cx and the d. So we have a bunch of terms on the left, a bunch of terms on the right. Now, combine like terms on the right, figure out the coefficients on the left, match the coefficients, and actually you are going to get a system of 4 linear equations in 4 unknowns, but this system is going to be very sparse. It's going, there are lots of missing spaces in there, and it's going to be actually very easy to solve. Probably easier than the system you would have gotten if you had just plugged in numbers. All right. I'll give you 20 seconds. Combine like terms, match coefficients. I'll give you 10 more seconds to match the coefficients. Write a system of 4 linear equations in 4 unknowns. In fact, I'll give you 20 more seconds. Okay, let's try to get some good form here. On the left, I want to clearly indicate the coefficients in parentheses. 2x cubed is 2 times x cubed. Now here, I want you to be very careful. Minus 1x squared. Remember, the coefficient on x squared is what? Is going to be -1. So it's actually better to write it as plus -1 times x squared. Because when we match up the coefficients, right, we're assuming that there are plus signs in front, and then the good stuff is in the parentheses, right? So we want to match up the contents of these parentheses here. And we don't have to worry about the fact that we have plus signs out here. If you see a minus 1x squared, make it plus a -1 times x squared. In general, if the coefficient is negative, okay, put the plus sign there, put the negative sign inside here, so then you can match automatically. Plus 2x, that's plus 2 times x, plus, well, 2 is 2. So aside from this whole plus -1 issue, well, plus -1 times x squared, you should be okay on the left. Now on the right, what's happening? Let's say we go in descending powers of x, which makes sense because that's what the left side is like, right? I would recommend going in descending powers of x, get a nice pattern. On the right side, the leading term is ax cubed, a times x cubed. In fact, I'm going to check these off as we get done with these. All right, so we have ax cubed. And then we have only one x squared term, bx squared, plus b times x squared. Plus, now we have ax and cx, right? ax plus cx. What's ax plus cx? Ax plus cx is going to be the quantity a plus c times x. So if you believe that, for example, 3x plus 4x is 7x, 3 plus 4 all times x, then you should believe that ax plus cx is the quantity a plus c all times x. It's like we're grouping these and we're factoring out the x. Plus, let's pick up the constant pieces. We have the b and the d. Plus, I'll put this in parentheses, b plus d will represent the constant term. Actually, it's going to end up being the 2, right? We're saying that b plus d is going to end up being the 2 over here. So these coefficients here are all in parentheses, and some of them have more than one term in them. But each of these coefficients will represent a real number. Okay, now we're going to match the coefficients, and we're going to get a system of 4 linear equations in 4 unknowns. So let's match them up. All right, so we start with, in fact, which order do I do them in my notes? Oh yeah, I just, I go from right to left. Actually, it goes through more, it goes through nicely that way. All right, the coefficient on x cubed here equals the coefficient on x cubed here. We're matching the coefficients on x cubed. A equals 2. That's how I got that thing, A equals 2. And then we match up the coefficients of x squared. B equals -1. You can see the benefit of just matching up the contents of these parentheses. We can now take it for granted that there's a plus sign in front. We made it so. Whereas if you had put -1 times x squared, oh, you could have easily made a sign error. plus, we match the coefficients on X. AS plus C is equal to 2. Finally, matching up the constant terms.
I should have said A plus C equals 2. A plus C equals 2.
You can think of the group B. You can think of the group B plus D as a term in some sense. Bottom line, B plus D equals 2. I guess that's red again. How about green? B plus D. Whether you think of this as one term with the parens or 2 terms in here, whatever, B plus D equals 2. So we match. Do this in black. Again, A equals 2, B equals -1, A plus C equals 2, B plus D equals 2. Oh, okay, well, when you do that, we get a system. I'll write it out. Type it out. Okay, here's a system. If you go right to left, A equals 2, B equals -1, A plus C equals 2, B plus D equals 2. We have a system of 4 linear equations and 4 unknowns, A, B, C, and D. But you can see it's a very sparse system. By the way, some people line up the like terms, but you can see it's a very sparse system, and it's very easy to solve. Right off the bat, A equals 2, B equals -1. We practically get those for free, right? And then, now with these guys here, it's not that hard because notice we have A plus C equals 2, but now wait a minute. We know that A is 2. Use that. Use that. So yeah, A plus C equals 2, but wait, A equals 2. A plus C equals 2, but wait, A is 2. So therefore, C equals 0. That's what we're here. A plus C equals 2, but we knew A was 2. Whoops. We knew A was 2. Plug that in. We get C equals 0. All right. And over here, very similarly, B plus D equals 2. B plus D equals 2. But wait, we know that B is -1. B plus D equals 2, but we know that B is -1. Add 1 to both sides, D equals 3. D equals 3. All right. So we use the top 2 equations here to help us solve these last 2 equations here for C and D. All right. A equals 2, B equals -1. We get again, A equals 2, B equals -1. We then get C equals 0, and then D equals 3. We're not done yet. Plug in. Oh, well, here's the system we are solving, right? But it's a very sparse system. So this big ugly guy here, right? This is the PFD form, all right? And remember, we got A equals 2, B equals -1, C equals 0, D equals 3. All right. 2, -1, 0, 3. So if you plug in these values for A, B, C, and D, you get this. What does that top become? 0x plus 3. Just plain old 3. And we're done here. We didn't do any long division, so we didn't have any extra pieces over here, like that x minus 1. This is it. Of course, you can switch the fractions. 2x minus 1 over x squared plus 1 plus 3 over the square of 3 over the square of x squared plus 1. partial fraction decompositions. That's it. Get practice. Here's the deal with PFDs. It's like sticking your feet in the cold water. You get very shaken at first, and you might freak out at first, but people get really good at these. So by the time you do like problem Z on my homework, I'm not really kidding that much. By the time you get through problem Z on my homework, you'll get a good feel for partial fractions. In fact, you might have more trouble reviewing the factoring along the way from chapter 2, right? Like 2.5. But you get good at this by the time you get to problem Z. On the final, on the Math 141 final, people normally do very well on these PFD problems. They get so much practice. They're good students. They get lots of practice, and they do these well. And they don't forget their grouping symbols. Good luck. A bit more in chapter 7 next time.
Now, the next video has optional material, but it's really cool stuff. And I'm going to point you out to these links over here. I'll copy them again. GeoGebra.org, including the 3D stuff for 3D graphing. Okay, so you might want to check these out. Okay, so let's take a look at this optional next video, which is cool stuff, though.
Hi, everyone. Let's wrap up chapter 7. The new stuff I talk about in this video is optional. Now, back in the early parts of chapter 7, we talked about solving systems of equations. The equations correspond to graphs, like the line in black here and the snake in blue. And we looked at these intersection points, which were solutions to the system. Now, in your calculus class, Math 150, you might ask questions like, what's the total area between the black graph and the blue graph? The area of this region plus the area of this region. And sometimes you can use symmetry. You need to know where these intersection points are in order to set up the integration. Use integration to find areas. And also, in Math 150, you're going to do things like take these regions, revolve them about the y-axis, let's say, and you're going to get a three-dimensional solid. And you'll use integration to find the volume of that solid. Okay, a few more comments. How do you graph x squared plus y squared equals 1? We saw him earlier in the chapter. That was the unit circle, was centered at the origin. But how do you graph an inequality? How do you graph x squared plus y squared is less than 1? You graph the interior of the circle. And how do we know to graph the interior? Well, you could test points. Remember, x squared plus y squared equals 1 corresponds to the boundary, which is dashed now. It's technically excluded from the graph. This represents the solution set to this inequality. Infinitely many points here in the interior. You could test points. So the origin, for example, 0, 0, x equals 0, y equals 0, 0 is less than 1. The origin, 0, 0, satisfies this inequality. And that helps tell us that we're going to shade in the interior. What about the exterior? Take a point like 2, 2. If you plug in x equals 2 and y equals 2, that's going to fail the inequality. You do not shade the exterior of the circle. So you could use a test point method. The origin satisfies the inequality. You shade the interior. The point 2, 2 fails the inequality. You do not shade the exterior. Or if you wish, you could test 1, 1, which is also in the exterior. By the way, what if you do is less than or equal to? You press is less than, and then right after that, the equal sign, you get is less than or equal to, and you get not just the interior, but the actual boundary, the actual circle. The circle will also consist of points that satisfy this inequality, this weak inequality, where you allow the circle. What's x squared plus y squared is greater than 1? That's the exterior of the unit circle. Okay, now let's consider GeoGebra, 3 dimensions. How do you graph x squared plus y squared equals 1 in 3 dimensions? It's not just a circle in the xy plane. You slide that circle parallel to the z-axis. In fact, the z-axis is going to be the axis of this cylinder. You get a cylinder. Basically, you have the unit circle, but then z can be anything above and below the unit circle. What about this? X squared plus y squared plus z squared equals 1. That gives you the unit sphere centered at the origin. You will definitely see these guys in calculus. Calculus with analytic geometry. By the way, if you replace this with is less than, you get the interior of the sphere. But GeoGebra doesn't do that, I don't think. All right, back to Desmos. How'd you graph x equals 0? X equals 0. That's the y-axis. But how do you graph x is greater than 0? That's everything to the right of the y-axis, right? All the points whose x-coordinate is greater than 0. How do you graph? Let's make it is greater than or equal to, then you pick up the y-axis. How do you graph y is greater than 0? What's y equals 0 first? How do you graph y equals 0? That's the x-axis. If you make this y is greater than 0, that's everything above the x-axis, where all the y-coordinates are positive. Notice right now that that this piece here is dashed, but if you make this is greater than or equal to, then this is no longer dashed. The whole x-axis is solid. Now, if you solve a system of inequalities, that means we need the overlap. What's the overlap between the red shaded area and the green shaded area? It's this dark green shaded area in quadrant 1, together with the non-negative x-axis and the non-negative y-axis. So all the points in here, including on these rays here, all of these points will give us the solution set for this system of inequalities, overlaps. Just like if we dealt with curves, we wanted the overlaps or intersection points between curves. When we're intersecting these regions, okay, we get a region of intersection here, which is the solution to the system of inequalities. We could do more. We could do something like x plus y is less than 1, for example, okay? And we can throw in some more inequalities, like, for example, linear inequalities. For example, let's throw in x is less than 2. Whoops, x is less than, how about 0.5? X is less than 0.5, and focus on this trapezoid in here. So we can throw in some more linear inequalities, and we get these regions of intersection with these linear boundaries. And that takes us to linear programming, which is covered in like Math 116. All right, in linear programming. So if you have a bunch of linear inequalities and you solve that system, you might get a region like this with linear boundaries. The x-axis could be production of guns. The y-axis could be production of butter, guns versus butter. Now, bear in mind, given the amount of money we have, we can only purchase certain ordered pairs, guns and butter. This is called the feasible region, what we can possibly buy. Now, the profit function at each point, okay, so each point corresponds to some profit. If the profit function itself is linear, then it turns out that the optimal point, the optimal production point, will correspond to a corner point, guns, comma, butter. Or you could have ties along an edge. That's a key principle of linear programming, which is a key process of optimization. How do you optimize profit given these constraints? So just some ideas from chapter 7.
All right, so before we get on to chapter 8, and I'm sure you knew what I was going to do here, but all right, chapter 8, movie time. All right. Hold on a second. Oh, okay.
Material in, well, your linear algebra class.
Okay, let's restart.
Hi, everyone. We're going to start chapter 8 with matrices and determinants. And we're going to see a lot of this material in, well, your linear algebra class Math 254, which is a very popular class. Many students take it, even some non-STEM people. So section 8.1 will cover matrices, what they are. Normally I'd play a commercial for the Keanu Reeves films, but we'll look at matrices. And in this section, we'll relate them to the systems of linear equations that we were talking about in chapter 7. In fact, we're going to build up to 3 equations in 3 unknowns. So first off, what is a matrix? A matrix is the singular form. Matrices is the plural. So again, the Keanu Reeves films might be the matrices. A matrix is basically an organized box or array of numbers, or maybe other expressions like e to the x or sine of x. In this chapter, we will typically assume that our matrices contain only numbers, although on the homework, you will see some exceptions. So for example, this is a matrix, and we use brackets here, large brackets, to block off a matrix, the entries of the matrix. These entries are also called elements. This particular matrix consists of 6 entries or elements. You see here that this matrix has 2 rows and 3 columns. So we say that this matrix has size 2 by 3 because it has 2 rows and 3 columns. In general, we say that a matrix is M by N, where M is the number of rows and N is the number of columns. We never switch these. And such a matrix would have Mn entries. So for example, a 5 by 10 matrix would have 50 entries. That's something you probably won't have to write out in a math class, but a math problem could hint at it, and you might use some general notation. So as another example, some of our favorite matrices are square matrices. A square matrix is basically an n by n matrix, where m equals n. I'll type this. An n by n matrix, that is where m equals n, where the number of rows equals the number of columns. So for example, this here is a 2 by 2 square matrix, or an order 2 square matrix. The bold-faced entries here lie on what's called the main diagonal. It extends from the upper left to the lower right. Every square matrix has a main diagonal, and we're going to see that's very important later on in this section. In a 2 by 2 matrix, the other diagonal, going from upper right to lower left, is called the skew diagonal. And I'll also mention that diagonal later on when we discuss determinants. A determinant is a number we relate to this kind of matrix. So how can we apply matrices to a system of linear equations? And in Math 254, you might see this kind of system, where we have a system of 2 linear equations in 3 unknowns. In our class, I won't really do this to you. I'll generally give you a square system, a system of n linear equations in n unknowns. But in Math 254, you might have this kind of non-square system, 2 linear equations in 3 unknowns, say, x, y, and z. By the way, I highly suggest you cross your z's when you write them on a piece of paper. Why? Because in Math 252, Calculus 3, or in linear algebra, Math 254, many students mix up their z's and their 2's. And I've taken off points because students mix up their z's and their 2's. So please don't mix them up. And I do suggest you cross your z's. By the way, I also recommend you curl your t's, give them tails, so you don't confuse them with plus signs. That's also an error I see, students mixing symbols up. And it's a shame to lose points that way. Students don't like that. They don't like losing points, especially because of silly mix-ups like these. Okay, now what's the idea behind writing an augmented matrix? I say augmented because we're also going to consider the right-hand sides here. Now, one benefit to an augmented matrix when it comes to solving systems is that we don't have to keep writing X, Y, and Z. So when you were solving systems before, if you didn't like having to manipulate X, Y, and Z all the time, if you really like numbers, then matrix solutions are the solution for you. If you really like numbers and you don't like variables so much, letters, then you may well want to work with matrices. Now, sometimes if these equations are written in kind of a strange way, then it's good to rewrite them, and to write them in what we could call a standard form, okay? Basically, something like of the form ax plus by plus cz equals a number. When we prep ourselves for setting up the augmented matrix, we often like to start off by writing an equation like this, even if some terms are missing. So look at this form for this equation here. Notice that all the variable terms are on the left side in alphabetical order. The x term, then the y term, then the z term. Later on in linear algebra, you try to get more professional because in principle, you could have more than 26 unknowns in theory. So you might write your unknowns or variables as x sub 1, x sub 2, x sub 3, and so forth. In principle, you could go to x sub 1,000 or whatever. And sometimes you could be asked theory questions where you might have to consider 1,000 unknowns or variables. And you may not be able to list them all out explicitly. Oh, by the way, if you have x, y, and z, if you need a fourth unknown, a lot of books wrap back to w, and I realize that might be confusing for people. And if this is confusing, then you really should start doing this form with the numbered subscripts, if you have a choice. There's only one constant term, and it's on the right side. So this number over here, it could be 0 or not. If this is a 0, then we call this a homogeneous equation. And also in a system, in this group of equations, it's helpful to line up the like terms vertically. And in fact, this was helpful back in the addition or elimination method back in chapter 7. So the system that I showed you up here, it's good to line up the x terms, line up the y terms, even a missing space for this missing y term, line up the z terms, line up the constant terms. So something like this. Now, as a challenge to you, try to write the augmented matrix. You're going to write the coefficients for x in the first column, the coefficients for y in the second column, the coefficients for z, notice I'm crossing my z, in the third column, and put the right-hand side, which is kind of like a vector. It's like a 1 by 2 vector here. Put
2
the
by 1.
right-hand side over here, consisting of these two right-hand sides. But be careful. You're writing down coefficients, and you may well make a mistake. I'll give you a shot to try to get this right. 20 seconds, go. Let's see if you made any errors. You know, it might actually be helpful to write these in. And in fact, as you solve a problem, you might want to write these missing coefficients and terms in. Over here, the plus z means plus 1z, not plus 0z. See, a lot of students look at this quickly and they see a blank here. Oh, I see a blank here. So their brain sometimes instinctively will say, oh, I guess I put a 0. I see a blank. No, the implied coefficient is a 1. So the thing is, if you tend to write things down quickly, you might really benefit from rewriting the system. Because if you tend to grab things that you see, right, then you might want to use this kind of form. Put plus 1z here. So you make sure you don't put a 0 up here. Over here, we have the negative 2x in the second equation, missing term. There's a blank spot there. That corresponds to the missing term, plus or minus 0y. That 0 helps. You can put a 0 here in the middle bottom. Again, over here, that's not a 0. What's the coefficient? It's a negative 1z. So
Well, the
it may be
coefficient,
a good idea.
the coefficient is negative 1.
Grab
The coefficient is negative 1, I should say.
pieces here to form your augmented matrix. It may be a good idea to insert coefficients of plus or minus 1 and 0. It's not necessary, but on the homework, as you practice on the homework, if you find that you mess up your augmented matrix without prepping this thing properly, then prep it properly. So part of the challenge here is knowing how much you have to prep your system in order to get the correct augmented matrix. To be safe, go all the way. Line up your like terms, put in missing coefficients and missing terms. Here's the answer. And by the way, if you're going to read these off directly, I know that many people are inclined to read these off equation by equation, and maybe that is better for some people. Let's look up here. Some people might think, oh, maybe I can read these off equation by equation, and maybe some people work better that way. But especially if you have it in this form here, where you put in the missing coefficients, it may actually be better to look at things column by column. Because then I think you're less likely to interpret like a 0 here, for example. All right, column by column. The column for x coefficients, 3 and negative 2. The column for y coefficients, 2 and 0. A lot of people miss that. The coefficients for z, 1 and negative 1. The right-hand sides, 0 and 3. Overall, what size is this matrix if you ignore the slash over here? Overall, this matrix is 2 by 4. What size is the coefficient matrix? That's 2 by 3. So because the coefficient matrix is not square, this is not a square system. It's not n linear equations in n unknowns. We don't see these so often in our class, but in Math 254, yes, you see these a lot, non-square systems. I can tell you right now that this system will not have one unique solution. The coefficient matrix consists of these coefficients to the left of this slash. The slash here corresponds to kind of these equal signs that separates these variable terms from the constant terms. The constant terms here on the right sides make up the right-hand side, the RHS. And you can kind of think of this as a vector or a thin matrix. It's like a vector. Or you could think of it as a 2 by 1 matrix. Sometimes we look at it one way, sometimes the other. Together, the coefficient matrix and the right-hand side make up the augmented matrix. I put a slash here to separate the coefficient matrix and the right-hand side. I know that Larson, for example, does not put this slash because he's afraid that when people perform operations, they forget to perform them on the right-hand side as well. That's up to you. If you tend to ignore the right-hand sides, maybe you're better off without the slash. I won't mark you off if you ignore it. Some authors do. Again, it may be faster for you to consider things column by column to retain accuracy. Why do we do this? One reason, the augmented matrix is an efficient representation of a system of linear equations, although the names of the variables are hidden. We hide the names of the variables. I like to label them at first so that near the end of the problem, I can refer back to them. Next up, we're going to talk about the kinds of operations we can perform on matrices, augmented matrices, in order to help us solve systems of linear equations. Next time.
Okay. Any questions before we proceed? Any questions? Any questions? All right.
Hi, everyone. Before we get to systems, let's talk about some legal moves or operations when we solve one single equation in one unknown. Take 2x minus 1 equals 5. What are some legal moves or operations? We can add 1 to both sides of an equation, and we get 2x equals 6. And then we can divide both sides of an equation by 2, and we end up with x equals 3. Remember, the answer to solve an equation problem is technically a solution set. It's the set consisting of the sole solution, 3. Now notice that the solution set applies to all 3 of these equations. 3 is the only value for x that will work in all 3 equations. And all 3 of these are equivalent equations. These are equivalent equations because they have the same solution set. In a way, they have the same graph, x equals 3. On the number line, x equals 3. Kind of like when we checked for equivalence back in trig. So the idea here is that you write a sequence of equivalent equations with the same solution set until you get a really nice equation whose solution set is obvious. At this point, x equals 3. It's obvious that 3 is the only real value for x that will make this equation work. In your Algebra 1 class, if you got up to x equals 3, you're basically done. But now in pre-calculus, we do want you to write the solution set. But really, this is obvious from this. Now, with systems, it's the same basic idea. Equivalent systems have the same solution set. This time, the solutions will be more like ordered pairs or ordered triples. And what are the legal moves or operations? They're called elementary row operations. I'll abbreviate them EROs. These are categories of legal moves or operations that allow us to write a sequence of row equivalent matrices, which correspond to equivalent systems, meaning they all have the same solution set. The idea is that we write equivalent or row equivalent matrices until we obtain one whose corresponding system and whose corresponding solution set is easy to find. By the way, the symbol for row equivalent matrices is this tilde or squiggle. So if an augmented matrix A is row equivalent to an augmented matrix B, we use the tilde or squiggle here to indicate row equivalence. It means that the system that A represents and the system that B represents are equivalent. They have the same solution set. That's different from equality. We'll talk about that later. So what are the 3 categories of legal EROs? And there are different ways to name them. One legal category of moves is row reordering or row switching. For example, if you have a system with these 2 equations, well, this system has a solution set. Solutions are of the form parentheses x comma y. Will the solution set change if you switch the order of these equations? No, we're looking for simultaneous solutions. It doesn't matter what order these equations are in. As far as maintaining the solution set goes, so you may as well switch these 2 equations and you'll end up with the same solution set. Your solutions will not change. XY works here if and only if XY works here. Which means when we do our augmented matrices, we can switch any 2 rows. In fact, we can permute the rows in any order, but make sure that each row here is represented in each row here. Make sure that each row here is represented in a row here. Don't miss any rows. So the augmented matrix for the first system looks like this. It's legal to switch the rows, and then you get this row equivalent matrix over here. Again, the symbol for row equivalence is this tilde or squiggle. We can reorder the rows of an augmented matrix in any order. And it's good to indicate what kinds of operations we're performing. So for example, if you're switching rows 1 and 2, it's really good to indicate that somehow. For example, books might do something like that. But you can pick whatever notation suits you well. Ideally, a notation that will inform a reader, like your grader or professor. In fact, on an exam, I tell students to write these kinds of notations so that it helps both the student and me to know what the student is doing if I'm not sure what the student is doing with the numbers. Especially if a student gets a problem wrong, I like to check the work, and this helps me a lot. Because imagine looking at a page full of numbers and not being given any instructions. It's like programming code with no comments. It's like, what are you doing? It's really good to indicate what you're doing. Do not reorder columns. Then you're mixing up the variables. You can reorder rows, but not columns. Row rescaling. We've seen something like this before. Let's say you have 1/2 x plus 1/2 y equals 3. You're itching to get rid of these fractions. How can you do it? Multiply both sides by 2. It's still legal. Okay, so if you do that, then you get this equivalent system over here. Same solution set. When you consider augmented matrices, we can multiply or divide through a row by any non-zero constant. Don't multiply by 0. So the first augmented matrix looked like that. It's legal to multiply the first equation, or the first row, by 2. Don't forget the right-hand side. If you tend to skip the right-hand side, maybe you shouldn't put the slash there. You could use notations like these. Replace the row 1, replace the old row 1. Okay, sorry. To get the new row 1, take twice the old row 1. To get the new row 1, take twice the old row 1. So 1/2, 1/2, 3 becomes 1, 1, 6. You can rewrite the second row. We often rewrite rows in this section. Be prepared for that. And we have row equivalents. Now, this third category, there's not a good name for this. Some books say row replacement. Well, aren't we always replacing rows? Some books, or I might say the row addition method, maybe. Basically, the idea is we can add a multiple of one row to another row. Basically, it combines row addition and rescaling. We can add a multiple of one row to another row, and we get a row equivalent matrix. For example, consider this system. When you write down the augmented matrix, it looks like that. Now, it turns out that when we perform our Gibbs method in just a moment, we love having that 1 in the upper left-hand corner, and we want to eliminate down. By eliminate, what do you think I want to put here instead of a -2? I want to see a 0 there, but we're going to have to deal with these other entries. All right, so what do? To kill the -2, I'd like to add a multiple of row 1 to row 2 so that the -2 becomes a 0. What should I multiply row 1 by before I add to make that a 0? I say double the first row, like before. Multiply the first row by 2. I like to do it in column form. So twice row 1 is 266. I'll put that in the middle row. Okay, we're changing row 2, right? We're changing row 2. So since we're changing row 2, I'll put the old row 2 up on top, which is the -2, 5, 16. The old row 2 goes on top, -2, 5, 16. Then twice row 1, 266 over here. And then to get the new row 2, you add. Remember, you can multiply by a negative number if necessary before you add in order to make a 0. Remember, just like with long division, it is much, much easier to add than to subtract. Like with long division, like with vectors, it's much easier to add than to subtract. -2 and 2 gives us 0. We like that. I put a smiley face here. Hard to draw smiley faces. Here, 5 plus 6 is 11. Here, 16 plus 6 is 22. Don't forget the right-hand side. Now, normally, we keep this row that we're rescaling by. We keep the old row 1, the 1, 3, 3. We like the 1 there. We like that. But then we replace the old row 2 with the new row 2, 0, 11, 22. And take a wild guess. What do you think we want here? What do you think we like having on the main diagonal? We like having 1s. We like that coefficient, which means we're going to do what with row 2? You're not allowed to subtract numbers through a row, but you're allowed to divide. We're going to divide by 11, or multiply by what? 111. Some books like to think of it that way. All right. And again, we have row equivalent matrices here. They're not equal. They don't have the same entries in the same position. Those are equal matrices, but these are row equivalent matrices. They represent equivalent systems. We use this tilde. Next up, we're going to look at GEBS, a technique that will allow us to solve linear systems of equations using augmented matrices and EROs. Next.
Okay, and by the way, after today, you could go on the homework up through 8.1, numbers 1 and 2. If you're brave, you could go further, but we'll do more examples next time. Okay, but after today, you can do 8.1, number 1 and 2 to play with these steps.
Hi, everyone. We're going to use GEBS, Gaussian elimination with back substitution. GEBS is my term, in order to solve systems of linear equations. And after this, you can do the first 2 problems on the homework to get some practice, and then I'll show more examples next time. Named after Carl Gauss, but the ancient Chinese knew it. Okay, let's assume in our class we have a square system, n linear equations, and n unknowns. So the coefficient matrix will be n by n. In our class, mostly 2 by 2 or 3 by 3. Write the augmented matrix, the first one, then use EROs to write a sequence of row equivalent matrices until you get one in the form we like. This is an example of what's called row echelon form. We'll talk more about that later. But one of our favorite row echelon forms is this. We're aiming for 1s along the main diagonal. We love that coefficient. 0, we love that even more. That corresponds to eliminating, right? Eliminating terms. 0s all below. And then these other entries can be wild cards. You could do it one way, your friends could do it another way, and you might have different entries in here. And the matrices could still be equivalent. In a way, this is the target. It's kind of like the right-hand side of a trig identity. Now, generally speaking, you try to correct the columns from left to right. Hopefully your matrix won't be this big, but the idea is that you want to get column 1 right, 1 and then a string of 0s, column 2 right, wild card 1, string of 0s, then column 3, and so forth. The idea is that, hey, if you've just cleaned the floor, you don't want a person with dirty shoes walking in. Why not? Because you don't want your good work to be undone, right? If your first column is good, you want to keep it good. Okay, now let's assume that you can achieve this form. Bear in mind, if the solution set is empty, for example, you cannot achieve this form. This form is only available if the system has one unique solution. Okay, so write the new system complete with the variables, your x's, y's, and z's maybe. Use back substitution to find the values of the unknowns. Write your solution. Presumably it's one unique solution as part of a solution set. Optional step, you can check. It's not required, but wow, you feel really good if your solution checks out. try out the first two problems on the homework. And by the way, you might want to quickly check each of your steps before proceeding. As you'll see, these problems are vulnerable to avalanche effects. Avalanche effects, my term. What do I mean by that? If you make a mistake early on, it tends to snowball. So you might want to check your steps along the way. A single mistake can have massive consequences that are difficult to correct. A check will make you feel really good. Again, you can try the first couple of problems on the homework. We'll do some more examples next time.
Are there any questions? So that ends the material for today. Okay, so you can do all the homework for chapter 7 and the first couple on 8.1. If you're brave, you could go further, but we'll start with this system next time. All right. Any questions? Any questions? I'll stick around for questions. All right. All right. So that's the class. Any questions? Any questions? So have a good night. I'll see you on Thursday. Well, quote unquote, see you on Thursday. Any questions? Any questions? Right. So now students are prepared to ask me questions. All right. So. All right. So I'm awaiting questions from students. All right. So for many of you, good night, but I'll stick around. Okay, awaiting at least one question from a student. Okay, so let's see, 7.1, number 3. Where's the, oh, that's my stats. Okay. Here we go, 141. All right. Okay, so, okay. What are the graphs of the equations? Okay, so we're looking at this over here. All right. All right, so looking at number 3 over here. All right. Okay, so I'm doing some purple. All right. So first of all, what are the graphs of the equations in the system in the usual XY plane? Well, if you take a look over here, right? Okay, you have x squared plus y squared equals 3/2. All right. Now you might remember, what is x squared plus y squared equals 1, right? What's x squared plus y squared equal to 1? Well, that's your classic unit circle. All right. This guy over here, x squared plus y squared equals 3/2. So if instead of 1, we have 3/2, it just means that we have a circle against the origin, but with a different radius. Okay, so the radius would be the square root of 3/2, because this is r squared, right? R squared is 3/2. So the radius would be the square root of 3/2. Okay, or if we multiply, multiply top 1 by 2. So we get the square root of 6/2. All right, but anyway, it's a circle, started at the origin. Okay, so the first equation gives us a circle centered at the origin. Okay, of radius this, but you don't have to go that far. Now the second equation, all right, I guess I should put the 3/2 over here, right? Okay. All right, now for the second equation, all right, y root 2 equals x squared. Y root 2 over x squared. It might be helpful to divide both sides by root 2. And you can think of it as y equals, and you can think of this as a coefficient, 1 over root 2 times x squared. And if you wish to rationalize the denominator, y equals the square root of 2 over 2 x squared. Bottom line is y equals a positive real number times x squared. What's the graph of that? Well, it's going to be a parabola opening upward. Okay, so the second equation is going to be a parabola in the xy plane opening upward. Okay, just like y equals x squared is a parabola opening upward. Root 2 is about 1.4. This is a positive number, less than 1/2. This is about 0.7, right? Root 2 over 2 is about 0.7. So it's going to be a vertical shrink, actually. If you want to go to Desmos, okay, here's y equals x squared. Here's y equals square root of 2 over 2 times x squared. Going from the red graph to the blue graph, it's a vertical shrink. You're squeezing it towards the x-axis. All right, but still a parabola opening upward. Okay, A and B. B, how many solutions does the system have? All right, well, here's the idea. So I'll do this in blue. All right, so we have a circle centered at the origin, and we have a parabola opening upward. How many intersection points are we going to have, right? How many solutions does the system have? How many intersection points do you see between the circle and the parabola? We're going to get, for sure, 2 points. In fact, they'll be symmetric about the y-axis. And by the way, the vertex for the parabola is at the origin, right? So we're going to get 2 intersection points, and they're symmetric about the y-axis. And then in part C, I actually have you work out the algebra. Okay, so we can work out the algebra. I should type in the problem here. So this is 7.1 number 3. All right, and then continuing over here, let's find the intersection points using the algebra. Okay, here the substitution method, because I can solve easily for y, right? In fact, I did it right here. We solve for y. Y equals this number times x squared. In fact, I could just say this. Okay, I can just say here that well, we have y root 2 equals x squared. Divide both sides by root 2. Y equals x squared over root 2. And since this isn't a final answer or anything, we don't have to rationalize the denominator. Okay, we don't have to rationalize the denominator. So I have this, and then I can plug this in. So we have y equals x squared over root 2. We can take this and plug it into y in the first equation. All right, I'll do that in blue. So from the first equation, we have x squared plus y is x squared over root 2, that's squared, equals 3/2. All right, x squared plus, when you square a fraction, you square the top and the bottom. The square of x squared is x to the 4th. The square of root 2 is 2, equals 3/2. All right. We can multiply both sides by 2. Over here, I distribute. I get 2x squared plus, and then when this 2 hits this 2, then we just get x to the fourth here. Bear in mind, you shouldn't strike the 2's here right now because the 2 also hits the x squared, right? Equals 2 times 3 halves. We just get 3. All right. Any questions so far? Any questions so far? All right. Now here, this is still a bit too complicated. We want a 0 on the right side. Okay. So let's do this. Descending powers, we have x to the fourth, then plus 2x squared, and then we subtract 3 from both sides. We subtract 3 from both sides. So then we get x to the fourth plus 2x squared minus 3 equals 0. And then you can do one of two things. You could do a substitution, let u equal x squared, the middle power. You could do that. Or you could factor it directly, old school. Okay, it does work out. Except instead of x's here, we have what? Instead of x's, we use x squareds. If that confuses you, you can do the substitution, right? The substitution will get you u squared plus 2u minus 3 equals 0. Right? Okay, so it's like an old school factoring, except we have x squareds here, not x's. All right. So split signs. Okay, positive 2u, that's going to be the sum of the cross terms. So, or positive 2x squared, right? So we're going to need a positive 3x squared and a negative 1x squared. That's going to work out. Okay. If worse comes to worse, you could use the quadratic formula for u, right? So then we have the zero factor property, all right? We have this product equaling 0, right? We have the 0 there. So we could say, yeah, I'm going to need a new panel. Okay, so we're going to say x squared plus 3 equals 0, or x squared minus 1 equals 0. Over here, subtract 3 from both sides. X squared equals negative 3. Is there any real number whose square is negative? Can the square of a real number be negative? The answer is no. This is a dead end. That's a dead end. There are no real values for x that'll make this work. But over here, add 1 to both sides. X squared equals 1. If x squared is 1, what can x be? Not just 1, don't forget, plus or minus. Negative 1 would also work. Right? Any questions so far? Because we've solved for x. We're not done yet, but we have solved for x. Any questions so far? All right. We're not done yet because what do we have to do? We have to find the corresponding y values. Fortunately, we have this relationship over here. All right. So now we're going to use the fact that we have y equals x squared over root 2. All right. Now, bear in mind, for both these cases, x squared equals 1. We knew x squared was 1. So y is going to be, for both these cases, 1 over root 2. X squared equals 1, right? So that means y equals 1 over root 2. That is root 2 over 2 after you rationalize. And this is the common y coordinate for both of these x coordinates over here. So what's our solution set? We have two solutions. One x coordinate is positive 1. The other x coordinate is negative 1. But the y coordinate for both these solutions, both these ordered pairs, will be root 2 over 2. And that should be your solution set. Let me see that it is. Yes. So the solution set consists of the ordered pair 1 comma root 2 over 2 and the ordered pair -1 comma root 2 over 2. Notice that, hey, let's look at Desmos to confirm that. Okay. So we have the circle x squared plus y squared equals 3/2. That's a circle. Okay. One intersection point is 1 comma square root 2 over 2. That looks good. That's the approximation, 0.707 for root 2 over 2. Also, we have -1 comma square root 2 over 2. Okay, that's this guy in black over here. Those are the two intersection points corresponding to the solutions of the system. All right. Any questions? Any questions? Technically, it's helpful to check, but since we have here y is a function of x, if you have a situation where you have y is a function of x, usually a check isn't needed. But in general, for a nonlinear system, it may be nice to check, but since we get y as a function of x, that's not as essential here. I think we're okay. All right. Any more questions or any follow-ups on this? All right. Do you think you might have any more questions, or should I come back in 3 minutes, say? All right. So I'll come back at 9:47. Okay. No more questions. All right. So we may talk later on. All right. So have a good night then. Good night. Take care.